Hello, I'm here with Joseph Polchinski, a theoretical physicist at the University of California, Santa Barbara, who is one of the authors of a recent theory about black holes that's been throwing the world of physics for a loop. Joe wrote Scientific American's April cover story about the theory, and we're here to talk over what it all means. I'll be asking some questions of my own, as well as some questions that readers have submitted. So Joe, your theory centers around something called firewalls. What are these firewalls?
So first, you've got to know what a black hole is. And so Einstein's theory says that if you get enough mass together, gravity will pull it and it will collapse down to a point. And anything that gets too close to that point will then be sucked in. The point of no return, the point past which you can't escape, is called the event horizon. And once you're past the event horizon, nothing, not even light, can get out. Now, Einstein's theory says that as you pass the event horizon, nothing happens. You're trapped, but you don't really know it right away until eventually you hit this singularity where everything gets crushed. But about 40 years ago, Stephen Hawking tried to combine our two great theories, general relativity and quantum mechanics. And he found that at the event horizon there was a problem. And his resolution of the problem was that Einstein's theory is fine, but that quantum mechanics, our theory of the very small, which explains behavior atoms and so on, that quantum mechanics had to be modified. And 40 years of trying to understand what Hawking said has not resolved the problem, but it's shown that if we try to mess with quantum mechanics, things get very bad. And so we've gone back to the idea that maybe Einstein's theory is wrong. So what my collaborators and I did was we took Hawking's original argument and ran it backwards. And we said, well, if quantum mechanics works, what exactly goes wrong? How bad is it? And as we followed it backwards, everything was fine until we got to the event horizon. But once we got to the event horizon, things couldn't be pushed any further, where Einstein's theory says there is a smooth space. Quantum mechanics seems to say no, that in fact there is a shell of high energy particles, maybe even worse than that, maybe the end of space itself, and that's what we call the firewall.
So this theory came out a couple years ago, and what's happened since you first thought of firewalls? Do they look even more plausible?
Well, it's been a lot of fun because although we felt the logic of our argument was very sound, we thought maybe we've overlooked something, and in 3 years it's caused a lot of consternation. I think no one's found a mistake in our argument. They've instead tried to look for other ways. It certainly is alarming. It bothered us, and it bothers many people, the idea that in a big astrophysical object, an object which could be huge, these little quantum effects could be so dramatic. But it's been interesting that in 3 years, a lot of new ideas have come out. People are really sort of, for the first time, pushing on quantum mechanics and asking, do we have to change it to make quantum gravity work? And maybe that's the answer, but we're not there yet.
So one of our readers has a good question to start us off with, and he says, how is there a fire around a black hole? And I think this might be an issue of semantics, but is there any fire in a firewall?
Well, so it's good. Yeah, actually, firewall is a funny choice of word because it also means something else on the internet. But the fire refers to these high energy particles existing in a region where there shouldn't be any. It's not combustion, but it still is basically high energy particles in a place where they shouldn't be. And they are, well, Hawking already told us that a black hole has a temperature, that it's a little bit hot. But the temperature is normally very low, and the firewall in some sense says that as you pass the horizon, the temperature becomes enormous.
And what would these mean? Would we be able to see them?
So it's interesting because the theory as it stands only, it's a problem. The problem is sort of fitting together the theory of the inside of the black hole with the theory of the outside of the black hole. And so it may be that you only see a problem if you actually jump in and see what's there. Now, that seems pretty exotic, but in some ways, the inside of a black hole is like our own expanding universe. The geometry of space is changing with time, and there's a singularity. So one reason we think so much about the insides of black holes is because they're a step towards understanding the origin of our own universe. But it could be that from the outside, the black hole looks perfectly ordinary. In fact, that would be my bet at this point.
Hmm. And so that really segues well to the next question, which is, what is inside a black hole? I mean, you mentioned a singularity. Is a singularity something we think really exists, or is that just a mathematical description?
Good. So if you take Einstein's theory and you just start calculating, you find that as you get closer and closer to the singularity in the center of the black hole, the curvature of space, which is like the strength of gravity, just keeps getting bigger without limit, goes to infinity. Our experience is if our equations give us infinity, we have the wrong equations, and we should look for better ones. And we have some ideas about that. But the surprise, and this again goes back to Hawking, is that the problem with quantum mechanics and gravity isn't just near the singularity where there's this obvious infinity. It reaches all the way out to the event horizon where things didn't seem so bad.
Right. So you've talked a lot about quantum mechanics and gravity and how they seem to collide here in black holes. How could firewalls and kind of probing into this idea help us finally reconcile the two?
So gravity and general relativity normally show up on very large scales, solar systems, galaxies, the whole universe. And quantum mechanics normally shows up on the microscopic scale, but they're both part of the complete theory, and there are some extreme environments where they both matter at the same time. An important one is the Big Bang. At the Big Bang, things were very small and very dense, and clearly understanding how the universe began really requires that we have a complete theory that incorporates both of these. It turns out that the black hole is another environment where they both enter. Now, because these environments are so extreme, our observational tools are very limited. But there's this notion of a thought experiment, which goes back to Hawking and Einstein and even Galileo, that one way you can test your theory is you can imagine some situation where, and you can ask, what does your theory predict? Or if you have two theories, do they agree? Which is what we're talking about here. And if the theories don't agree, then we have a clue. We have a puzzle and we have a clue. And the black hole has provided several important puzzles and clues as to how to fit these theories together.
Right. So one of the coolest parts of the firewall idea for me is how you talk about it arises from entanglement. So remind us all what entanglement is and what that has to do with firewalls.
Entanglement is the weirdest thing about quantum mechanics. Quantum mechanics says that microscopic physics is very different from the physics we see. And one thing about this is so-called the uncertainty principle. You can't be sure where particles are. That electrons don't make nice, simple orbits around atoms, but they're kind of clouds. But the even weirder thing about quantum mechanics is this notion of entanglement, which links two or more particles together. And in some sense, quantum mechanics, it's like throwing dice. With entanglement, imagine you have two dice, and each of them is numbered 1 to 6. Imagine you throw the first die, comes up a 1. You throw the second die, it comes up a 6. And you do this again and again. You find that whatever the first die comes up, the second one always comes up so that they add up to 7. So these two dice are linked in some mysterious way. And in quantum mechanics, particles can be linked in this way. And it's actually something which is, well, it's been, again, Einstein, going back to him, he was bothered by this. And these days it's getting a lot of attention because it can be used for sort of for codes and security and for computation. But also it seems to be tied up with the way that space-time and quantum mechanics are connected. Entanglement, you can think of entanglement as kind of providing the hooks that hold, these entanglements are the hooks that hold space together. And what's happening with the firewall is that the hooks get broken, get unhooked. And that's what produces maybe the energy, maybe just the end of space.
So one of our readers asks, according to your work, firewalls result from the energy released when particles break their entanglement, like you just mentioned.
Yes.
Does that mean that energy was input to entangle the particles in the first place?
No, it's a little bit the other way around. That is, if the system is kind of relaxed to a state of low energy, then the hooks are there, and it's the breaking of the hooks that costs energy. So I wouldn't have said it quite that way.
Okay, so the hooks are the normal everyday.
The hooks are the normal everyday thing, and it's the breaking of them that is the problem. Yes.
Okay. And could we ever harness the phenomenon of entanglement to study what happens inside a black hole? For example, is it possible to take two entangled particles and send one into the black hole and watch what happens to the other one to understand what's happening on the other side?
Yeah, the black holes have been an endless source of sort of thought experiments of this sort. That is, you want to try to probe the state, the quantum behavior of the black hole. And there are many different ways to do it. And one of them is just what you said. You start with an entangled particle, you keep one, throw another one in. And in fact, you can do this over and over again. And so what will happen over time is that you will build up an enormous entanglement between the particles you've kept and the ones that you've thrown in. And in fact, in some ways, this is the origin of Hawking's argument, because there has to be a black hole kind of has a maximum entanglement. There's a limit to it. And it seems as though this process would let you exceed that. So in fact, what your reader asked about is one of the ways that we've tried to probe, theoretically, how a black hole will behave.
Okay. And so this leads us to some general black hole questions to begin with. First of all, how do we even know that black holes exist?
They've now been observed. So first of all, Einstein's theory predicts them. If they don't exist, the theory is wrong. But happily, this much of the theory has been very nicely confirmed. We actually know that out there are sort of two different classes of black holes. There are black holes that are a little bit heavier than the sun, that form when supermassive stars burn out. And we can see them because even though they're now collapsed, they're still sucking matter in. And we can see the matter being sucked in. We can see it glowing and emitting X-rays. So that's one kind of black hole. The second kind is more like the mass of a million or a billion suns. And these form right when the galaxies are born. The galaxies are born out of a cloud of hot gas. Gravity pulls it together into clumps, and the center of these clumps become black holes. And this is really cool because when you look at the center of our black hole, at the center of our galaxy, rather, you have to look in the infrared to see through all the dust. You can see stars. Over a period of years, you can see stars moving in circular orbits. They're orbiting around something, but there's nothing there. And so there is some very incredibly massive object, again, the mass of a million suns, which is emitting no light, but we can see its effect on those stars. And so we know that there's one of it's quite spooky, except it's not. It's just science. seeing these stars, traveling in these circles, and so we know that there are these two kinds. So Einstein's theory, well, it's now been confirmed in many places, but maybe these are the two most spectacular.
So what is the death of a black hole like?
Well, it's Hawking who said that they can die because they can emit radiation, and he was excited because as they get older, they actually get hotter and brighter, which seems backwards, but it's the way it works. And so the very last instance, the black hole would emit a burst of hot radiation. And so his hope was that maybe during the Big Bang, a very large number of fairly small black holes would form, and such that they would be burning out kind of today on a continuous basis, and we'd be seeing these bursts of radiation. So far, no sign of that. It seems like maybe the early universe wasn't quite chaotic enough to produce these primordial black holes that Hawking wanted.
But that doesn't mean they don't undergo this phenomena at some point.
No, it just means that doesn't mean that the phenomena doesn't exist. It just means that the universe hasn't provided black holes of the right size for us to observe. Right.
Got it. So what's the largest black hole ever found?
Well, so I couldn't put a precise number on it, but it's of the order of 1 billion suns. And the interesting thing is that although black holes themselves are black, again, if they find themselves in the center of a cloud of gas, they start pulling it in, and that gas heats up as it falls in and starts radiating. And so, in fact, some of the most spectacular objects in the universe are actually powered by black holes, by the energy released during the infall. Things like quasars and jets. So yeah, about 1 billion suns. Pretty big.
Mm-hmm.
Yes.
And how common are black holes in the universe? Are there many right around our cosmic?
So I actually went to Google this morning because I didn't know this number, and the nearest known black hole is about 1,600 light years from us. So that's not actually. I actually might have thought it would be closer. That the nearest star is a few light years. This is almost 1,000 times that. So perhaps there are closer ones which just are dark and have not been seen. Or maybe it's simply that the stars that are massive enough to collapse into black holes are sufficiently rare. Yeah, the details of astrophysics observation is not my specialty, but I follow it as a very avid fan.
And what do you think of this idea that has been floating around, that black holes, I guess mini black holes, could be contributing to dark matter?
Well, so good. So dark matter is really cool. The fact that originally there was a suspicion that stars were orbiting too fast in galaxies, and now observation has improved so much that one can map out the dark matter by watching how it bends light, and also map it out by how it affects the expansion of the universe. So it's clearly there, and it's clearly something which, well, again, it's massive but doesn't have many other properties. Black holes as the actual source of the black matter, my understanding is that it's largely been ruled out. And again, this is not an area where I'm an expert, so I can point to specifics. But the suspicion there is more that it's something much smaller, a massive particle of some type. Yeah. So out of my expertise, but that's my understanding.
Okay. So one of our readers has an interesting question about Einstein. He says Einstein once stated that a clock at a black hole's event horizon would go at the rate of 0. Does that mean that Einstein thought that time to a distant observer slows to a stop at a black hole boundary?
Absolutely. So Einstein is the one who pointed out that time is relative and clocks move at different speeds depending on where they are and how fast they're moving. And what he just said can be understood. So the light rays, once you're behind the horizon, light rays can't escape from the black hole. If you're just outside the horizon, they can escape, but they take a very, very long time. So as you fall through the black hole, if you're sending out a series of light pulses, say, the closer you get to the horizon, the longer it takes for that pulse to escape. And so the observer sitting far away sees your pulses or your clock slowing and slowing and slowing. Indeed, it will have to slow to zero because you actually fall through, Einstein's theory says, fairly quickly. It doesn't take a really long time. But it takes longer and longer for the person outside to know that.
So at least death is quick for you, although distant observers, it looks like you're dying for a very long time.
Well, yeah, although I don't want to give away any spoilers here, but if you've seen the movie Interstellar, it might not be death. I enjoyed that movie because, again, not giving not to. I don't think it exactly matches our current theories about the insides of black holes, but I like the idea that the inside might be an interesting place.
Hmm. Right. And did you think that some of the ideas it raises about, time travel, is that's allowed in physics? That's still on the table?
No, really not. I shouldn't say no. I shouldn't say no. Large parts of that movie, the physics was done, very carefully because they especially the Kip Thorne, the physicist who, put it together, wanted the science to be good, but there's a certain point past which we don't know, and let's just say they took the most interesting point of view about what might be true. Well, I can't say no, it's impossible, but it really requires, it's a speculation.
Hmm. And based on what we now know about firewalls, I mean, I don't think firewalls were in the movie, but even if you could travel through a black hole, wouldn't firewalls then mean that you can't?
Good. So the firewall, in some sense, is a worst case scenario. It says that the inside of the black hole is not the smooth space that Einstein said. But another way to think about it is that when you hit the firewall, you kind of dissolve into, I want to call a bunch of quantum bits, just sort of little ones and zeros that live on the surface of the black hole. And the likely interpretation of this is it's a very bad thing. You would just cease to really exist in any organized way. But I'm willing to entertain, just for the purpose of a movie, and also just because it's fun to think about, the possibility that these ones and zeros, these bits on the horizon, maybe have a more organized structure that would actually be interesting in some way.
Huh. And traversable.
Well, traversable, maybe entering into a new form. Again, I wouldn't bet on it, but I'm willing to suspend disbelief.
Oh, that's pretty intriguing. I like that idea. So here's a question. A lot of people compare the singularity inside a black hole to the singularity of the Big Bang at the beginning of the universe. Is there any corresponding firewall scenario at the Big Bang?
Good. So exactly. The short answer is we don't know. But it's interesting that the expanding universe also has these horizons, these points of no return. And in fact, all the time as the universe gets larger, distant stars basically recede from view. They begin receding from us so fast that we will never see them again. And so it's sort of like with the black hole, the horizon is kind of, we're on the outside of the horizon. With the expanding universe, we're on the inside of the horizon. It surrounds us. Now, this seems to make a fairly large difference. I mean, in some ways, it's the same thing, but in terms of the actual details, it makes a fairly large difference. The actual argument that we use to argue for the firewall applies to the black hole case where we're on the outside of it. It doesn't apply directly to the cosmic case where we're on the inside. So So the short answer is the firewall directly. Um, well, it would be surprising if it existed for the cosmic horizon, but the hope, of course, is that what we learn by understanding how the firewall works, or maybe why it's not there, will teach us how the Big Bang worked. I mean, I'm not deeply attached to the firewall. What I always say is that my brain believes in the firewall, my gut doesn't, because my gut is very disturbed by the idea that there is this smooth space that Einstein predicted isn't there. But every logical argument that I can understand seems to point to it. It would be so. So if in fact the logic is wrong, it means that there is some deep new idea that we're missing. And so I think life would be more interesting if the firewall went away, because it would mean we had some deep new idea. But at this point, I'm not taking bets. I'm just trying to see what works.
So tell us what's next. What are you working on these days?
So very much on this same thing. In fact, very precisely on the connection between entanglement and the existence of space. It's kind of fun because, I mean, the way you make progress on these very hard problems is you try to break them down into smaller problems that you can get your hands on. And so some students and colleagues and I and some competitors at other universities are making these little models of space, which are really very simple. They're just sort of 4 or 8 little bits linked together, something you could write down on a piece of paper. But you can test out different ideas for how the quantum linking and the emergence of space works, and we'll see. It's the firewall, right or wrong, is pushing us to sort of ask these new questions, and so that the kind of thing I just described is typical of what I'm trying to do, to make smaller models of these very complicated things that we're talking about.
And is this model something on a computer?
No, it's a good question. That is one reason for working with just 4 or 8 is you can do all the mathematics by hand. If a problem gets so big you have to put it on a computer, I'm never happy, because then there's the input and the output, and I can't keep. I like something simple enough that I can follow all the steps. But indeed, I mean, it's interesting that, I mean, there's this thing called quantum computation where people are trying to harness entanglement to build much more powerful computers, and there's a huge overlap of the mathematics between that field right now and understanding black holes.
And how about using computers to simulate a firewall? Has anybody tried supercomputer simulation?
Well, yes, people have, but the question still is, part of the problem is we don't. The real reason we're pursuing this is we don't have the complete theory, and so we don't actually know what we should be simulating. And so you can simulate this model and say, yeah, it looks like a firewall, but maybe that was the wrong thing to simulate. So there's been some of that, but I think we still need to figure out what the theory is.
So those of us who are interested in this kind of stuff, but who are not physicists, we're very impatient for news. So when do you think this whole firewall question might be settled? Is this something that's going to come to a head in the next few years?
So it's an interesting question. It's hard to predict these things. Hawking's original puzzle is about 40 years old, 1976. And for 20 years, people kind of went around in circles with it. And then in the mid-90s, there was a series of discoveries that gave us a much clearer picture of a quantum black hole. And then maybe almost 20 more years went by, and then the firewall, and related ideas. The firewall is only one of a number of different threads connecting entanglement in space. But what's happened in the last 5 years, again, is that there's been, maybe 3 years, this set of ideas coming together, which tells us there's a connection between entanglement and space. And so there's the feeling that we're on the threshold of a new understanding on a timescale of a few years, maybe less. But we'll have to see. We'll have to see. So there are fun things happening. There are a little to convey to the public. They're a little abstruse. Again, I kind of talked about these models of bits in space. About 10 years ago, this is one of the events that kicked all this off. Some quantum theorists pointed out that when something is thrown into a black hole, this is before the firewall. Hawking said the information was destroyed. We now believe the information is not destroyed. They pointed out the information actually comes out very fast. Now, I don't know, it's a little bit technical why, but it was exciting to the theorists because we thought, how can this happen? And it actually started the train of thought that led to the firewall. So I'm not sure what to say except that we're working hard and we think we're onto something exciting.
Well, we'll definitely be staying tuned. So thank you so much, Joe, for taking the time to answer these questions and for writing the article. And everybody who hasn't read it should go check out the April Scientific American cover story.
Thank you, Clara, very much. It's been a lot of fun.
Take care.